Hello. Okay, sorry. I did not realize I was muted that whole time. Oops. Yeah, I will be monitoring the Slack channel. Also, feel free to unmute yourself and ask a question or Slack me. Either is fine. But don't be shy asking questions because this is only for internal use, and there's very few people who are going to watch this, and it's likely that they have a similar background to you and might have a similar question. So stop me whenever. This is for you guys. But yeah, without further ado, let's jump into this. We're gonna talk about Zerocheck today, um, and we're gonna cover the first three modules: the mathematical preliminaries, why Zerocheck matters and where it comes from, and then the Zerocheck to sum check reduction. Um, then next time we'll talk about like the sum check protocol, and we will forget about like where the Zerocheck came from or where the sum check came from, and we'll just talk about like the sum check protocol and how it works behind the scenes. Um, Finally, we'll talk about like performance optimizations and smart things you can do to make sum check faster and better. But today we're going to focus on this part, which is the math preliminaries to understand everything, honestly, and also like the basics of Zerocheck, like why it matters in the context of proof systems and how we can change our Zerocheck instance into a sum check instance. So this math part, I will admit, is a little bit dense, but I think that learning this properly will pay huge dividends in your understanding of proof systems, because these are really very, very important building blocks, not just for understanding Zerocheck, but for understanding like a lot of the stuff that we do, whether it's additive NTT, whether it's like Frobenius, whether it's like lookup arguments or Zerocheck. um, Understanding these math preliminaries well is going to be crucial to being able to, decode the complicated things that Ben and Jim say when talking about proof systems. So, if there's anything that I can stress, it's that, definitely review this content, especially these math preliminaries, because it'll be super, super helpful for your understanding. With that said, we're going to dive into it. And yeah, like I said, disclaimer, this first part will be a little bit dense, but it's important to like do your best to try and be familiar with this material because it'll pay huge dividends if you're able to grok the math part. So yeah, my goal is to teach the concepts behind Zerocheck and to jargon bust the mathematical language behind Binius. And I'm gonna try and make this hard material as accessible as possible, but it's still going to require effort on your part to try and understand this. That said, any questions along the way or after the fact, I'm very happy to answer them. So please don't be shy. So let's start. First, let's talk about what a multilinear polynomial is. It's just a polynomial that is linear in every single variable. So what that means is like if you were to look at this and if you were to pretend like x1 and x2 is constant, is this a linear polynomial? The answer is yes. Similarly, if I were to pretend x0 and x2 are constant, is this a linear polynomial in x1? And the answer is yes. It's got to be linear in every single variable. That's what makes a polynomial multilinear. The second example is not multilinear because it's not linear in x0. We have an x0 squared term in here. The next definition is like a monomial. So what is a monomial? It's like a product of powers of indeterminants with a coefficient. Another way to think about it is a monomial is literally just a polynomial with one term. So a monomial would look something like this. A binomial might look something like this, bi as in two terms, mono as in one. A polynomial can have like any number of terms. But generally, a polynomial is just like a sum of a bunch of monomials. And yeah, monomial is a term that you'll definitely hear a lot, and you'll hear Ben use it a lot. So what is a monomial? It's just like one of these guys. So one of the terms in a polynomial, pretty much. Cool. So again, we have some examples. This is a monomial. This is not a monomial. It's a binomial or a polynomial. A polynomial is kind of like a rectangle, and a monomial is like a square. Oh. Cool. So now we have some other definitions, which are quite important. The individual degree.
What's F? Sorry, where A0 belongs to F, what's F?
Oh, great question. F is like some field. So specifically, like polynomials are defined over some field. Their coefficients come from some field, and then these indeterminates are like just symbols. So A0 here, like imagine it's like 3. So 3x0, x1 cubed, x2 to the ninth. In this case, our field could be like the rational numbers or the real numbers. Cool. Yeah, so the next definition we have is that of an individual degree. So what is the individual degree of a specific variable xi in a monomial? Well, it's just like the power of xi that's in that expression, that monomial expression. There's a formal definition. Don't worry about that for now. You can read that on your own time. But basically, if I were to look at this monomial, for instance, the individual degree of x0 is 2, the individual degree of x2 is 9, and the individual degree of x1 is 0. There's another concept, the total degree in a monomial. Total degree in a monomial is just the sum of all the powers. So here we have like x0 squared, x2 to the ninth. Total degree of this monomial is 2 plus 9, 11. Finally, we have the individual degree of a polynomial, or the total degree of a polynomial. Both of these are basically like the max of the monomial individual degrees, or the max of the monomial total degrees. So let's look at an example. We have this polynomial, f on 3 variables, which consists of 2 monomials. So if I ask what the individual degree of x0 is of this polynomial, I can say the individual degree of x0 in monomial 1 is 1. The individual degree of x0 in monomial 2 is 2. Therefore, the individual degree of x0 in this polynomial is the maximum of 1 and 2, which is 2. We can follow a similar procedure for the total degree. The total degree in this monomial is 4, 1 plus 3. The total degree in this monomial is 2 plus 2 plus 2, which is 6. So the total degree of this polynomial is the max total degree of each of the monomials, which is the max of 4 and 6, which gives me 6. Great. Any questions so far about total degree, individual degree? Okay,
Nope.
cool. All right, NX, did you have a question?
Nope.
It seemed like you unmuted for. Okay, no worries. Cool. So back to multilinear polynomials. Another way to describe a multilinear polynomial is it's a polynomial whose maximum individual degree is 1. That means the individual degree of each of these guys can be at most 1. Great. Yeah, let's talk about bases and vector spaces. So if you're familiar with a vector space, basically a vector space is something that is defined over a specific field, and you need some operations on, like, vector space is basically like a set with a couple of special operations. So one of those special operations is like scalar multiplication, being able to multiply a vector with a field element. Another operation is like being able to, say, add 2 vectors together from the vector space. If you're not familiar with like this linear algebra, then don't worry about what this means generally, and we can take a look at some examples of vector spaces. Most of the vector spaces that we'll be talking about are polynomial vector spaces. So for instance, if I look at the set of degree less than or equal to 3 univariate, which means single variable, polynomials, where the coefficients come from the rational numbers, Q means the rationals, then that's actually a vector space over the field of rational numbers. That's a mouthful, so I'll say that again. If I look at the set of degree at most 3 univariate polynomials with coefficients from rationals, that is a vector space over which field? they're rational numbers. And so we can talk about a basis for this vector space. And we'll see what a basis is in just a second. The set 1x, x squared, x cubed is a set of 4 vectors from this vector space. You can see that each of these are polynomials with rational coefficients that are of degree at most 3. So these are vectors from this vector space such that every element of this vector space can be written as a linear combination of basis vectors with rational coefficients. This property is called spanning. Another property that bases must satisfy is that they're minimal. I can't remove any of these elements and still have the spanning property to be true. So what does that mean? Like if I had like a generic element of V, in this case, I had something that looked like a0 plus a1x plus a2x squared plus a3x cubed, then it can be written as a linear combination of 1x, x squared, x cubed. And what are the coefficients for that linear combination? It's exactly a0, a1, a2, a3. So this almost kind of looks trivially true. That just so happens to be because we represent polynomials in this basis, like generally, like usually 1x, x squared, x cubed. But note that that's a representation choice, and we'll talk about that a little bit more. Another example of a vector space is like the set of multilinear polynomials on, let's say, 3 variables with coefficients from t iota. So now I'm using like some more notation because I'm trying to, get you comfortable with Binius notation. T iota is a field. It's specifically the iota tower field, and our tower fields are binary tower fields. So to say a thing, T iota is like isomorphic to f2 to the 2 to the iota. And to say another thing, like every finite field of the same size is isomorphic to one another. That's just a fun fact. So the basis for this vector space would be this 1, x0, x1, x2, blah, blah, blah. And this is of dimension 8. So what is a dimension of a vector space? It is literally just the number of elements in a basis. And there could be multiple bases. Like I said, it's a representation choice, which basis you choose, but they will all have the same cardinality or size. Yeah, so here's like what I said written down. Every element of the vector space can be uniquely written as a linear combination with coefficients from the field F of basis vectors in B. B is the set of basis vectors. Great. So these examples.
So I remember from my algebra classes,
Sure.
Unilinear polynomials, but I haven't seen polynomials with several coefficients. So yeah, I'm
with
very
several
comfortable with the example on the left, but the one on the right is new to me.
That's fair. Yeah, that makes sense to me. I think that this is, people have seen this more often and this less often. But you'll eventually get comfortable with this one too. Yeah, this one is definitely more normal for people. Cool. So I'll give more motivation when I think useful for examples like this. But these two examples that we have here of vector spaces are the bases that we gave are called monomial bases. Why are they called monomial bases? Well, if you look at every single vector, basis vector, it is itself a monomial. Same thing here. These are each monomials. So we call this a monomial basis. And really, it's like the standard basis, like what you'd expect the basis to be for these polynomial vector spaces. So why am I talking about basis and stuff? The reason I'm talking about it is because we can actually represent elements of a vector space, so vectors in the vector space, by their coefficients with respect to a specific basis. This representation of elements, just using their coefficients, is sometimes referred to as a coordinate vector with respect to a specifically chosen basis. So for example, I could write a multilinear polynomial f of x0 up to xn minus 1 in this form, where it's like b0 times 1, b1 times x0 plus dot 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 plus b to 2 to the n minus 1 of all of these. Or I could represent it as just the coefficients b, where these coefficients are with respect to the monomial basis that I had above this. Okay. Basically, if I multiply b0 by 1 and b1 by x0, blah, 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 the last b by the last basis vector here, and then I sum all those things up, that's basically the same as f. Now, generally, if I want to evaluate a polynomial, right, at a point r, and to make this clear, r here is like a bunch of things because there's more than one variable, then the way I should do this is I should evaluate the basis polynomials at this point r, and then I should dot product it with the coefficients. These coefficients are just like field elements or constants. They don't depend on any of the x's, right? These are just values. So I evaluate my basis polynomials at the point r, and then I dot product it with the coefficients. So I do something like this, right? And that gives me the evaluation of f at r. Cool. Any questions here? All right, I will continue. For example, okay, sorry, here. Now we're gonna move on and we'll introduce this fact. A multilinear polynomial can be uniquely defined by its Boolean hypercube evaluations. What does that mean? If I'm given some function, not necessarily a polynomial, just some function that maps inputs to outputs, and it maps an input which is on the Boolean hypercube domain, so 0, 1 to the n, or like n bit strings, you can think about it, to values that live in some field, then there exists a unique multilinear polynomial whose evaluations agree with f. For example, if I know that f is a multilinear on two variables, and I know some of its evaluations over the two-dimensional Boolean hypercube, then I can tell you that there is exactly one polynomial that f can be, just given these 5 facts. Because of this fact. Uniquely identifiable by Boolean hypercube evaluations. So now let's see why that's true. If I say f of x0, x1 has to be equal to something, I can do this like Lagrange interpolation trick, which maybe or maybe not you haven't seen before. But what I'm doing is I will say that f is equal to this whole expression. Now, what is the like meaning of this expression? Think about what happens if x0 and x1 are both equal to 0. Then this term, this factor here, will be equal to 1. This factor will be 0 because x0 is 0. This factor will be 0 because x1 is 0. This factor will be 0 because x0 and x1 are both 0. So f of 0, 0 is going to be equal to a0 times 1 plus a1 times 0 plus a2 times 0 plus a3 times 0. So f of 0, 0 is going to just be a0. Similarly, like f of 1, 1 this will become 0, this will become 0, this will become 0, this will become 1. So f of 1, 1 is going to be a0 times 0, a1 times 0, a2 times 0, plus a3 times 1. Basically, like each of these guys are like indicator polynomials. When you plug in like x0 and x1 are either 0 or 1, they're like an indicator polynomial that gives you a factor of either 0 or 1, depending on whether it's a specific input. So I can do this trick, which is basically called Lagrange interpolation generally. And if I simplify it, like I expand this, then I get something that looks like this: a0 times 1 plus this times x0 plus this times x1 plus this times x0 x1. And when you see this like fully expanded version, you look at the thing and you're like, oh, okay, I believe you that this is a multilinear polynomial because like you recognize this form of 1, x0 x1 x0 x1. You can see that these are just a bunch of values, coefficients, and these are like monomials that are clearly multilinear. Therefore, I believe you that this thing is now multilinear. So yeah, I mean, I can say b0 is equal to a0, b1 is equal to this, blah, blah, blah. And now I can represent this multilinear polynomial as b0, b1, b2, b3, and say that this is a coordinate vector in the monomial basis. Or I could represent this multilinear polynomial as a0, a1, a2, a3, and say that this is the coordinate vector in the standard Lagrange basis. So as it turns out, this set of polynomials, this, and this, also forms a valid basis, four-dimensional basis, for the vector space of multilinear polynomials of two variables. So that's interesting. This is a basis. This is also a basis. They're two different bases. This is a monomial basis, and this is the Lagrange basis, is what we call it. So let's elaborate on what Lagrange basis means. If you fix an input domain, in our case, that's going to be the Boolean hypercube. A Lagrange polynomial, LV of x's, is an indicator polynomial such that if x is equal to this v, then we will output 1. And if x is not equal to this v, but x is still in this input domain, then this is going to output 0. Cool. So if we look at this, I said that this is a Lagrange basis over the two-dimensional Boolean hypercube input domain for the vector space of two variable multilinear polynomials. And this here is exactly the Lagrange polynomial, the indicator polynomial for whether x0 and x1 are both zeros. If x0 and x1 are both 0 or 1, this evaluates to 1 if and only if x0 and x1 are both 0, 0, and it evaluates to 0 otherwise. Similar here. Similar here. Cool. So sometimes this is written as what we call a tensor product. The endianness of this is wrong, but let's ignore that for a sec. Sometimes this is written like this, which is like a tensor product expansion. Now, what is a tensor product? Tensor product is something like this. If I have a vector AB and I tensor it with a vector CD, then what I get is I get a vector that looks like this: A, C, A, D, B, C, B, D. So what's going on here is if I have like 1 minus x0, x0, and I tensor that with 1 minus x1, x1, what I'll get is I'll get this vector that looks like this: 1 minus x1, 1 minus x0, x1, x0, 1 minus x1, x0, x1. You'll see that this is not exactly the same thing as this. That's because of an endianness problem, and maybe like Ben and Jim should have written this as like I equals n minus 1 to 0 going backwards. But basically, for all like intents and purposes, this tensor expansion is basically a tensor expansion of the 1 minus xi's. Maybe I should make this clearer by making these like this. Cool. Any questions about this? So last note before I take questions is the Lagrange basis coefficients are exactly the evaluations of the polynomial over the input domain for which the Lagrange basis is defined. In our case, n-dimensional Boolean hypercube. So going back up to here, these are the Lagrange basis coefficients. So this is Lagrange basis, these guys. These are the coefficients in the Lagrange basis. And A0, A1, A2, A3 are literally evaluations over the Boolean hypercube. Any questions about this?
So the previous definition for input domain D, this one went a bit over my head, and reading it again, I don't know what it means. Can you go over it again?
Sure, yeah. This is a little bit more general than what we need it to be. But basically, if you fix a specific input domain D, so let's fix one, like the Boolean hypercube, which means like bit strings, n length bit strings, 0, 1 to the n, basically. So fix that input domain. Now a Lagrange polynomial with respect to that input domain is basically like LV, where V is like some specific bit string, and then it takes in like n variables. And basically this polynomial is an indicator polynomial. And what that means is it has like a specific property that if this variable bit string is equal to this fixed bit string, then it equals 1. And if this like takes values that are different from this fixed bit string, then it equals 0. So specifically, like up here, if I were to pass in, let's look at these examples actually, right? If I were to pass in some bit string, so the specific bit string for this is 1, 0, right? If I were to pass in something other than 1, 0 into x0 and x1, that's a bit string, then this will equal to 0, right? Like let's say I pass in 0, 0, then this equals 0. But if I pass in exactly the same fixed bit string for which this Lagrange polynomial is defined, 1, 0, x0 is 1, x1 is 0, then this will evaluate to 1.
Clear, thank you.
Okay, cool. Yeah, it's basically just like a way to turn on or turn off like one of these terms, right? Like if I pass in 0, 0 here, I want to turn all of this off and turn only this A0 on. If I pass in 1, 1 here, I want to turn all of this off and turn on only A3, which was like my evaluation at 1, 1. Cool, yeah, so that's a Lagrange polynomial. Great. Now, let me talk about something called the equality indicator, which is a multilinear polynomial on 2n variables. This is also an indicator polynomial. Basically, what it means is if you take in a 2n length bit string, if the first half is the same bit string as the second half, you get 1. If the first half is a different bit string than the second half, then you get 0. So this is like a function actually. This indicator function is defined over the Boolean hypercube. Then there exists a unique multilinear polynomial that agrees with those evaluations over the hypercube. I can actually write down the formula for what EQ looks like. Let me create a new page so I can do that. I'll do it here. for instance, EQ of like x0, y0 is equal to this 1 minus x0, 1 minus y0 plus x0, y0. Let's do EQ on like x0, x1, y0, y1. So this is like when it takes in 2 variables. What if it takes in like 4 variables? Then it's equal to 1 minus x0, 1 minus y0 plus x0, y0, all multiplied by 1 minus x1, 1 minus y1 plus x1, y1. And so on and so forth. The pattern continues. Why does this work? Well, let's convince ourselves that the first one works. If x0 is equal to y0, then this should be equal to 1. And if x0 and y0 are different, this should equal to 0. So if x0 and y0 are both 0, this is 1, this is 0. Good. X0 and y0 are both 1s. 0, 1. That's good. If one of them is 1 and the other one is 0, both these terms go to 0. Now, similarly, what's happening when we expand it to like more variables to make sure the first half of the bit string is equal to the second half of the bit string, we're basically checking like this term is 1 if and only if the first bit's matched. This term is 1 if and only if the second bit's matched. And this like multiplication of something that's either 0 or 1 in Boolean logic is kind of like an AND. So this is basically saying like, did the first bits match? And this is basically saying, did the second bits match? And then this is basically like a logical AND. So I can actually write down a multilinear polynomial on 2n variables that has the property that if you look at inputs that come from the Boolean hypercube, so bit string inputs, it tells you whether the first half of the bit string is equal to the second half of the bit string.
So I have a question.
Yeah.
Where does this multilinear live? What's the field?
That's a great question. It doesn't really matter what the field is, because if you actually look at the definition, what are the only field elements used? It's just like
0 and 1.
Yeah, exactly, which every field will have. But we usually say that the equality, like multilinear, lives in like whichever field we actually care about. Is it t iota? Is it like t tau, etc.?
Yep. Thank you.
Cool. All right, let's see. Cool. So this equality indicator, multilinear, is actually going to be really important. One note is that like all polynomials, it can be partially evaluated or to specialize. Like you can fix some of these inputs to be like all zeros or all ones or whatever, and you can partially evaluate the polynomial by specializing some of the variables to specific values. Cool. So let's talk again about evaluating some generic multilinear polynomial at some specific point R. What does that look like? Before we talk about that, we need to make another definition. The multilinear extension of a function f is denoted as f tilde. So f could be just like some function, not necessarily a polynomial, just a function that maps inputs to outputs. That's what a function is, right? And so the inputs live in the Boolean hypercube domain. The outputs live in some field. So it's mapping some inputs to some output values. F tilde is a multilinear polynomial that takes in n variables, n values for the variables, and outputs some value. Okay. So we said that there's a unique multilinear polynomial that agrees with some given evaluations over the Boolean hypercube. What does that look like? So we can say that f tilde of these n variables is equal to the sum taken over every single hypercube element, so every single bit string of the EQ function, multilinear, of Vy multiplied by f of V. So again, V is just like one of the bit strings, and we're summing over all the possible bit strings, all 2 to the n of them. And what are we doing inside the sum? It's EQ of Vy multiplied by f of V, which is just some value, some constant. Okay? You should convince yourself that this f tilde is indeed multilinear, because every single term in it, every single monomial in it, is going to be multilinear, because we know EQ is multilinear, and this is just a constant. You should also convince yourself that if we were to pass in some value for these y's that was a bit string, it would agree with this function f on the same bit string value. Why? Let's say I were to pass in like f tilde of all zeros. Then this term here would be 1 if and only if V was all zeros. 2, right? That means that every single other term would basically be zeroed out, and the only thing that we'd have in this whole thing is like 1 times f of 0, 0, 0, etc. Plus 0 times something, plus 0 times something, plus 0 times something, plus 0 times something. Now, a really neat trick when you have something that looks like this expression and it's really complicated to know whether it's actually doing the right thing or not is to check 2 multilinears are equal if and only if their evaluations agree over the Boolean hypercube input domain. So is f tilde really the multilinear extension of f? Question mark. We know f has some multilinear extension. Is this expression that we wrote down a valid expression for the multilinear expression of f, extension of f? The answer is yes, because if we plug in some hypercube element here, so some bit string as the input here, we can look at this and assure ourselves that we will actually get the right answer, f of the same value, because of these indicators doing their job.
I have a picture in my head. Do you have a picture in your head?
No, I do not. You want to draw it?
I always draw pictures when I teach. But yeah, I mean, why? Actually, I guess there are kind of a couple questions floating around, right? The first is, does f hat actually restrict to f identically on the cube, right? Or in other words, is it in other words, does f hat and f agree on the cube? A. B is like, is f hat multilinear? Right. So if both of those are true, then f hat is a multilinear extension. And then you have to ask if it's unique. This is more or less the proof of existence of multilinears, right?
Mm-hmm.
As for uniqueness, what do you do for that? You basically subtract them or something, or what?
Yeah.
And then they would have kind of non-equal Lagrange coefficients, right? So that thing should not be identically 0.
Yeah.
But I remember Thaler doing something much weirder and more complicated. So maybe I'm missing something.
Yeah, I'll think about that.
But anyway, I keep interrupting your recordings, which
No,
I
it's fine.
think it are meant to be more like lectures than office hours, is what it seems to me.
Yeah, these recordings are going to be only used internally, and after I leave, like it's going to be you and Nikita and Jim and other people explaining these concepts. I don't think this will be a one and done sort of thing. Like I think people need to keep coming back to this.
So the picture I have in my head is again a polynomial with only one variable. So what I remember is like if the polynomial is degree 1, and then it's equal on 2 points, then the two polynomials are equal. Or if it's a polynomial of degree 2 on just one variable, if it's equal in 3 points, then it's equal. So this is just the same thing, but applied to multilinear polynomials, right?
Yeah, pretty much. Yeah.
It's similar to that, but there's a slightly more specific thing that is being said here, which is that essentially that given, so let's think about univariate, right? If I have some domain of n points in the x-axis, and I have prescribed y values for each of those endpoints. The question is, can I come up with a polynomial of degree less than n that interpolates through all of those points, right? And the answer is yes. So this is basically a multivariate, multilinear analog of that fact, right? Is that fair? Which is related to the fact you said, but not exactly the same fact, right?
Okay, and now if you allow yourself to, I mean, not be multilinear, if you allow yourself to go square, cube with several of the variables, then it's no longer true, right? This definition is no longer true.
Something like this will be true. It's just going to be more complicated, right? So now, how should I say this? Basically, there's a domain that uniquely characterizes a polynomial. So in other words, in the univariate case, if I pick n points, then that uniquely characterizes a polynomial of degree less than n. If I allow degree n or more, then it exists but stops being unique. So I can still come up with a polynomial that interpolates these endpoints, but I can actually come up with 2 or more or something like that, right? Whereas if your degree is too small, then uniqueness holds, but existence could fail. So you might not even be able to find one at all. So in the multivariate case, you have something similar, right? Like if you allow higher degree, then the problem of existence becomes easier and the problem of uniqueness becomes harder. So if I allow higher degree things, then there are tons of polynomials that interpolate, that restrict in the right way to the cube or something, right? So another way of saying it, the flip side of that coin is that in order to recover uniqueness, I now need a bigger domain, right? So instead of just the cube, I need some kind of weird domain where instead of like a 2 by 2 by 2 cube, it's like 3 by 3 by 3 or something like that. And then I get existence and uniqueness, right? So the clean way of thinking about this is that for each number of variables and each degree constraint, then you can come up with some domain that is a unique specifier for polynomials. In the multilinear case, that domain is the cube, but in the L variate degree 2 case, then you need some other kind of domain as a unique specifier, like some 3 by 3 cube or something like that, right?
Multi-quadratic case.
There would be what, 3 to the n basis elements if it's the square case?
Yeah, it would be 3 to the n or something, right?
Yeah.
I think, yeah, it should
It
be
would
that.
be like 0, 1, 2 Cartesian product.
Yeah, exactly.
10 times.
Yep.
Cool.
Do you mind if I draw a quick picture or what?
Yeah, sure. Go ahead and draw that. Let me see what next. While he does that, I will say one more fact, just highlighted, that if you take EQ and you specialize like half of the variables to be some hypercube point, then that is literally one of the Lagrange basis polynomials. So for instance, the Lagrange basis for two variable multilinear polynomials looks exactly like this. can see that this is exactly the same thing as this. Let me zoom out so you can even see it clearer. EQ of x0, x1, 0, 0 is the same thing as 1 minus x0 times 1 minus x1, which is the same thing as the Lagrange basis polynomial for the fixed vector 0, 0. So that's why it's super useful. If we take the like tensor expansion of the equality indicator, and look at all of its hypercube evaluations, we basically get the Lagrange basis polynomials. Any questions on that? When Ben's ready with his picture, I'll let him screen share for a sec.
Should I go for it?
Are you ready? Okay, let me
Yeah, it's not. I would rather draw it live if that's
Oh,
cool.
okay.
That way you can kind of see what I'm actually doing.
see if you can screen share.
Yeah. All right, so what does a polynomial, a multilinear on two variables look like, right? Well, we have our kind of domain, our independent variables live down here in the plane, and then our dependent variable goes up here, right? So the two-dimensional cube obviously looks like a square, so L equal 2, okay? So what I want is the ability to take prescribed values on this cube and come up with a polynomial that with a multilinear rather that attains those prescribed values. So what does it look like to write down prescribed values? Well, I don't know. It looks like picking maybe this should be 5, okay, and maybe this should be like 7 up here. And right, so what is a function? I mean, remember we just to state basic things, right? And this one's going to be 3. Right, so a function, remember, is just a way of associating a number or value to each point in the domain. So this, what I just wrote down, is a perfectly good function, right? Does anybody disagree with that? Yes, no? Okay, but this is not a polynomial, it's just a function. It's just a specification of numbers. It has no algebraic structure, right? So the whole point of what Kabir is just saying is that given this just raw data, can I write down an algebraic actual polynomial, in fact, a multilinear polynomial, whose restriction to the cube agrees with this raw data? Okay, so again, this is like Lagrange interpolation, but multilinear instead of univariate. All right, so so the key is this Lagrange basis, right? So these are kind of like elemental atoms polynomials, right? That I can use as building blocks, right? So this is the one that is 1 at the origin and is 0 everywhere else, okay? And I also have one that is, you know, it's 1 at this point and 0 everywhere else, right? And you see where this is going, right? So I'm now going to have one that's 1 here, 1 here, and 0 everywhere else. And finally, this guy. So these are my axes. This is the origin, right? Origin. So this is the x0 axis. This is the x1 axis. Something like that, right? So I have these 4 things. These are what the Lagrange basis polynomials look like, right? And really, these are not just functions on the cube, but really multilinear. So they kind of extrapolate Like this is where the drawing is in danger of getting dicey. But each of these you should think of as something like a plane that goes on forever, right? And that restricts to the cube in the way that is given, right? So this one goes down like that, and kind of up towards the camera. This thing goes like this, down like this, right? So it makes sense for me to be like, what is, so let's call this, you know, chi of 0, 0. This is chi of 0, 1, chi of 1, 0, chi of 1, 1, right? And these things are functions that I can evaluate at any point, right? Because these planes go off forever. So it makes sense for me to ask, what is the value of chi1 at, you know, this point, right? So this thing is way off somewhere. This is like, I don't know, 2, or no, what is it? Like 5, 3 or so, I don't know, something like that, right? I can evaluate chi of 1, 1 at any point, 5, 3. That makes sense. Okay, so if I want to use these as my building blocks and build something which is multilinear and looks like this, then what do I do? Well, who can say it?
You add them together.
Wait, what?
You take
But
linear
it's five
combinations.
times.
Yeah.
5 times the first one,
Yes.
1 times the second one, 4 times the
Exactly.
third one.
So yeah, exactly. So I add them, I take a linear combination, I scale them. So both of you, what you said. So I take basically, you know, 5 times this thing. So I can sort of scale this and then that's supposed to be a times 5. You know, this one is going to be times 1, right? You get the idea. And right, so I can always scale and then I can always add, and then, you know, what do you know? Next thing you know, you get the thing you want. So so this is some kind of plain looking thing. And okay, so this proves theorem, you know, MLEs exist, right? We just proved that. How do we know that these are multilinear? You know, I don't know, maybe that's like an exercise, right? Like basically these things are themselves multilinear. This looks like 1 minus x0 times 1 minus x1. This thing looks like, what is it going to be, like x0 times 1 minus x1, something like that, right? Have you guys seen these expressions?
Yeah, we just looked at them.
Oh, shoot. All right, and then there's a uniqueness question, which is actually a bit annoying because it depends on how you define things. I can stumble through that if you guys want, or I can hand it back to Kabir.
Up to you guys.
We're already 1 hour into this.
Okay,
So
let
think
me
of it.
let me continue then. We're almost done with the math section, which is the hardest section for sure. Let me go back into the screen sharing. iPhone, iPad. Let's do it back. Okay, here we go. So finally, right, let's take basically what Ben was saying. We can take a point that's not necessarily in the hypercube. It wouldn't make sense to try and ask what the function evaluated at that point was, but it does make sense to ask what the polynomial evaluated at this point is. what we can do is we can evaluate our Lagrange basis at that point. And yeah, then we can dot product it with the Lagrange basis coefficients, and we're able to evaluate the multilinear polynomial at that point. And that's happens to be a multilinear polynomial that agreed with the function input outputs, where the inputs were over the Boolean hypercube. So now I want to talk about one last important thing, which is polynomial identity testing for multilinears and univariate specifically. So zero testing is asking the question like, is this polynomial equal to 0? And when I say 0, I mean like identically 0. It's like literally the polynomial whose definition is 0. One answer you can give is like, yes, if and only if it's 0 everywhere on the hypercube. This is a fair answer. But I mean, that's kind of a lot of things to check. Another thing you could say is like, yes, with high probability, if evaluated at a random point, it's equal to 0, where this random point is sampled from some like cryptographically large enough domain. The reason this is true, like in plain English, is that if f is anything other than the identically 0 polynomial, then it can't have too many roots. And a root is like an input where f evaluates to 0. So if f is 0 at a random point and f is not equal to 0, what's the chance that you got unlucky and you picked like one of these roots? Very, very low. We can build on zero testing and make a new primitive called equality testing, which basically checks like, are two polynomials the same polynomial? One way you could do that is like, okay, are they the same over the hypercube for multilinears? But that's kind of annoying. Another way you can do it is we can subtract these two multilinears, get a new multilinear, and say, hey, is the subtracted multilinear equal to 0? Now, like, the reason behind this, like, there's some notes here which are basically like explaining how many roots you can have if you're a non-zero polynomial. In the univariate case, you can have at most d roots, where d is like the degree. In the multivariate case, you can have, well, the probability that you pick a root is at most like d, which is the total degree of your multivariate polynomial, over like the size of the field where you're picking the random coordinates from. D here is like the total degree. In the multilinear case, the total degree is always going to be at most n. You can think about like this size of field k, where k is like the cryptographically large enough field, as being like, that size is like 2 to the 128, let's say, and n is like a number like 30. So 30 over 2 to the 128 is like an insanely small number. So the probability that if you do this like equality testing or zero testing by checking random points, checking evaluations at random points, the probability that that sort of leads you astray and makes you accept something that wasn't actually 0 is actually very tiny. And the verifier is happy with that because of how much performance he'll be able to eventually win. So that's the end of the first section, the math prelims. Are there any questions about that? Because that is the most important section.
So you mentioned the equality of x0, x1, and y0, y1, etc. at some point in the middle of the lecture. And then did you never mention it again? Or did I miss it later?
So the main thing that the
this is EQ.
Yeah, EQ is
Okay.
Yeah.
So it was used later on. Okay.
Yeah, here's the main part where it's used, like talking about the multilinear extension definition.
Okay.
Cool. All right, so let's talk about why Zerocheck matters. The setting is that I want to prove to you that I know something, like let's say the 10th Fibonacci number. One way that might seem contrived at first glance of how I could prove this to you is to say that, hey, I know a matrix, an 8x3 matrix, where certain things are true. Right. First thing is that, and so what is this 8x3 matrix, first of all? You'll notice this first column basically corresponds to the ith Fibonacci number, The second column is like the I+1th Fibonacci number, and the third is the I+2th Fibonacci number. So if I can convince you that the first two numbers that I have are 0 and 1, which is like the base case of Fibonacci, and I can also convince you that the last number in this matrix is 34, which is what I'm claiming is the 10th Fibonacci number. And I can also convince you that all of these diagonals contain the same number. And finally, I can also convince you that the ith plus I+1th Fibonacci number is equal to the I+2th Fibonacci number. If I can convince you of all those things, that should be enough for you to be satisfied that the 10th Fibonacci number is indeed what I said it was, 34. So the things I need to prove are some like boundary constraints, like inputs and outputs, show you that I started with 0 and 1 and I ended with 34. I need to show some copy constraints, which are that like all these values on the diagonals are exactly the same. And finally, I need to show you some gate constraints, which are basically saying that like the ith plus the I+1th Fibonacci number is always equal to the I+2th Fibonacci number. So if I can do all those things, the verifier is convinced. Let's focus on these gate properties. Right, so here we can define like a polynomial that takes in 3 variables corresponding to the number of columns, and it's a plus b minus c. So if everything was kosher, then it should be the case that the gate constraint evaluated on any particular row should give me 0. The 2 plus 3 minus 5 should give me 0. Now, so the verifier's goal is to check that the gate constraint evaluated on every row is equal to 0. So we can write down like a vector of evaluations of the gate constraint. Like let's keep this in our head for a second. We don't actually like write it down or anything, but like imagine that someone had written down a vector of evaluations of the gate constraint over every single row. In order for the verifier to be satisfied, this should be a vector full of zeros. Cool. So how is the verifier going to check that this vector would be a vector full of zeros? One way that they might do that is to like literally look at the entire trace and evaluate every single row with a gate polynomial. That is very slow. It also isn't very zero knowledge-y if you're trying to use zero knowledge. But there's actually a better way to do this, which basically amounts to if you were to look at this vector and you were to imagine that this vector was not a vector of values, but actually defining a function, mapping a row index or a bit string to a value. So like a Boolean hypercube element to a value. Now this is a function where the input domain is a Boolean hypercube. Okay, then we know that there's a multilinear that has those exact evaluations over the Boolean hypercube. We would want to see that that multilinear is exactly the 0 multilinear. And we could use our polynomial identity testing fact to help us. So specifically, like if we were able to evaluate the multilinear extension of this function d at a random point r, if that gave us 0, then we'd be pretty certain that this function was just a function that any hypercube point you give it, any row you give it, it outputs 0. So that's sort of what we're going to do. And it's like kind of this contrived procedure, but this is sort of the process that we'll take. And as Ben points out, the reason that this is actually more efficient than just checking every single row to see if the gate constraint is true is because of polynomial commitment schemes and the magic that they afford us. Basically, we can think about each and every single one of these columns as actually being a function which maps some Boolean hypercube element in the input to some value in the output from the field. So if we think about each of these columns being functions, then we could think about the multilinear extension of each of these functions. And then we can ask questions that seemingly don't make sense, like what is A evaluated at like 37, 54, 99? We can only do that if we have the multilinear extension of A. So by having a polynomial commitment scheme that allows us to give the verifier a short proof of what A or B or C's multilinear extension evaluated at a random point would be, the verifier will have an easy way to actually evaluate what the multilinear extension of D would be at a random point in better than linear time, linear in the size of this trace. So polynomial commitment schemes make this magic possible and make it so that the verifier has a more efficient way of checking whether this function is a function where any Boolean input gives you a 0 by doing a 0 test on the multilinear extension of this function. That was a mouthful, so I'm going to stop there for questions. Did that make sense? Okay. Going to take the silence as you have no questions and maybe need to let that simmer. But yeah, this is basically what we call Zerocheck. So again, just restating, the idea is we pretend like this function D, like a vector of values that are associated with some inputs is basically a function. We pretend like the multilinear extension is actually, we pretend like we have a multilinear extension, which is basically the multilinear extension of this function. And then we're going to 0 test this multilinear extension at a random point. And if it's equal to 0, then the verifier is satisfied that the gate constraints are all valid for every row. Now we define a protocol called Zerocheck. Zerocheck is an interactive protocol where a prover convinces the verifier that a multivariate polynomial evaluates to 0 over the hypercube. So here H is defined like this. It is a multivariate polynomial. And we want to show that for every single hypercube point V, every single bit string input, H evaluated on that bit string gives you 0. Now there's a common misunderstanding. I'm not saying that H is necessarily 0, because H is not necessarily multilinear in general. Remember this fact that if you are all zeros over the Boolean hypercube, then you must be the 0 polynomial is only true if the polynomial is multilinear. You can very much have a multivariate polynomial that happens to be 0 on all those points, but is non-zero elsewhere. If like your gate constraint was something that looked like this, for instance, then we can no longer guarantee that H is multilinear. However, if you look at H's evaluations over the Boolean hypercube, and think about that function, there is a multilinear polynomial that agrees with those evaluations. We'll call it D tilde. And this multilinear polynomial, we can 0 test as a proxy for testing whether H was 0 everywhere over the hypercube. So what we're really doing in Zerocheck is we're checking whether we're given a multivariate polynomial, and then we define a multilinear polynomial that agrees with the multivariate polynomial over the Boolean hypercube. And we're going to do something that mathematically is equivalent to checking whether this multilinear polynomial at a random point is in fact 0. But that's sort of like a behind the scenes math detail of what we're doing. The reason,
So
like,
quick question. For the x0 up to xn minus 1 for the multilinear extension, those are not from the Boolean. Those are not Boolean, right? They could be from the underlying field.
Exactly, yeah. Like when I define the multilinear extension, you can think about it as like let's say that D was the function from like 0, 1 to the n to f. You could, if you'd like, think about the multilinear extension as being of this type. It takes in like the x's can be anything from the field. It doesn't have to be 0 or 1 anymore. Basically, it allows me to evaluate at places that I wasn't explicitly given the evaluations for. Make sense?
Yep.
Cool. So, yeah, that's the end of section 2. Any questions about like the purpose of Zerocheck in Snark protocols? All right, let's accelerate to the final section. This is the Zerocheck to sum check reduction. So mathematically, what we want to do is zero test this multilinear polynomial d tilde. And the way we'll do that is we'll sample a random challenge vector from some cryptographically large field. This is T tau, the Tauth tower field, binary tower field. And we're going to check whether this multilinear polynomial evaluated at this random point is in fact equal to 0. That means what we want to show is that this expression is equal to 0 because these two things, this is equal. So we want to check whether this expression is equal to 0. Okay. If this expression is equal to 0, that's the same thing as saying that this is equal to 0. Definition. SumCheck is an interactive protocol where the prover convinces the verifier that a multivariate polynomial, h bar, has hypercube evaluations that sum to a claimed total S. So the prover wants to prove to V that h bar of V is equal to S when summed up over all the possible bit strings V. Cool. So you can probably already see that if we want to check this is equal to 0, using a tool that does something like this, we could set h bar to be equal to this right here. Okay, it's a little subtle. Let's say that we started with some polynomial that looked like this. D of xy is equal to eqyx times h of y. We could eliminate the y and try all the possible bit strings y and get something that looks like this. This is the multilinear extension of D, the original D that we had, the function. We could also eliminate the x and have something that looks like this, right? Like we specialize x to be some specific value, and then like everywhere we had an x, we replace it with the special value r. Right. So if we do this, then what we'd like to do, what we do from going from here to here to eliminate the y is we like sum up over all the possible y's. What we did from here to here was we specialize the x. Okay, so let's just say that like h bar y is equal to this exact thing. Now let's say I want to get rid of the y. So let me sum up over all the possible y's. Then that changes like h bar y into like this just expression, which no longer has any variables in it. Now this expression is basically the same thing as like taking this expression and changing the x into an r. So what we end up getting is something that looks like this sum is exactly the same as this sum, which is exactly the same as checking whether d tilde r is equal to 0. So I'll let you guys verify the math on your own time. But basically what I'm saying is the procedure to complete the Zerocheck to sum check reduction is you're given a multivariate h, you sample a random challenge, you define h bar as this new multivariate, which is equal to this, and then you output a sumcheck instance that this new h bar summed up over the entire hypercube should have evaluations that come to 0. And the mathematical reason behind why this works is because sum checking over this h bar over the entire hypercube, taking all those sums, is exactly the same statement, exactly the same expression as the expression you need in order to evaluate d tilde at R. So like the mathematical thing we wanted to do really was evaluate d tilde at R. That's exactly the same mathematical expression as summing up over h bar over the entire hypercube. So that's how we do our Zerocheck to sumcheck reduction. Given a multivariate, we create a new multivariate that you might notice has one higher max individual degree than h, and we output this sumcheck instance. The multilinear extension thing is just something that exists in our head to justify the mathematical soundness of this protocol. Also, a lot of information and a mouthful. So I'll let that simmer. Do you guys have any questions about that?
Yeah, like in this kind of setting, I always try to ask just kind of sanity checks, right? Like, why is this complete, right? So say that you're an honest prover, what happens in the case of the honest prover, right? Like, I don't know if we want to go whole questions during the live recording, but yeah, I mean, if I were teaching a class, I would stand there and wait until somebody said something about that, right? Because like if you know, there can be cases where the audience is like one step behind or like 10 steps behind, and you don't know which of those two you're dealing with until you ask stuff like that, right? So anyway.
It's fair. Yeah, this is a lot of information to try and pack into an hour. That's what I'm realizing.
Yeah, fair.
Yeah. Okay, but this is basically the last thing that I wanted to say. This like Zerocheck to sumcheck reduction. And the reason that we did this reduction is because the next class what we'll be talking about is just sumcheck. We're going to start with sumcheck instance, and we're going to talk about how you prove that sumcheck instance and why that protocol is both complete and sound. And we're sort of dropping all the prior context of the Zerocheck and gate constraints and where it came from in the snark. We'll also assume some familiarity with the mathematical preliminaries that we discussed at the beginning of this session. But yeah, once you're kind of familiar with this, then we have the tools and background necessary to just like start at the level of a sumcheck instance and talk about the details of how we would prove that. I would say, yeah, this might take like a couple passes to be comfortable with this material. Definitely reread the notes, rewatch the lecture, ping me or Ben or whoever whenever you have any questions. And yeah, like Thursday, there's more office hours. We can talk about any questions you have from this stuff. But try and, if you have the bandwidth to, try to be familiar with this as much as possible before we go into the next part, talking about the internals of sumcheck. This is the sort of repetition helps.
I have one question. For Binius, we restrict H to a multivariate polynomial of degree at most 2, right?
I don't know if it's a hard restriction, but yeah, we've definitely talked about doing stuff like that.
But do you know if it's if that's what's currently implemented? Like,
I'm not sure. I don't think there is anywhere in the code base where it forces you to be degree 2, to my knowledge.
oh, okay.
But it's possible that like when we write the constraint programming API and like put stuff on top of it, we'll make sure that things are degree 2. When we talk about the next lecture, like how sumcheck works, you'll see why it's useful to have this H, the Zerocheck instance H, be something with like low maximum individual degree.
Okay.
Basically, there's like a trade-off And the higher the degree of this H, the less efficient the sum check procedure will be. In the next like class as well, like we're only going to be talking about vanilla sum check, like literally 0 optimizations will be made. So if you see something that disagrees with the code, recognize that the code has done optimizations.
Makes sense.
Yeah. Cool.
Thank you.
All right. Yeah. Again, if any questions, feel free to ask. I'll post this like recording ASAP, so you guys will be able to refer back to it.
Future prof in the making, you the man.
Thank you, Ben, for the help. Appreciate it. Please join these things when you can.
Yeah, I know. I've been pretty spot